Good evening. Take two. So I tested, made sure the audio actually works this time. So I'm picking up where we left off. We said Newton's first law is an object at rest will tend to stay at rest, while an object in motion will tend to stay in motion. So Galileo was the first one who initially said this, but Newton is the one who did additional experiments to double check and retest, and he's ultimately the person who took it from an idea to a law, right? So ideas, and I addressed this last time, pushing a dead car, if it's not in neutral, if you've ever tried to just push on a car that's parked, you can kind of get it to rock, but the cars itself don't roll unless you're in neutral, right? And even in neutral, it takes a good amount of effort to get the car rolling. If there are no brakes on, you really have to do some good pushing before that thing starts to roll, because the object wants to stay at rest. Okay, famous one, talked about it before, when you play like Jello or whatever with your brother or sister or friends in the car, someone takes a hard right, you guys fly to the left. Why is that? Because your body wants to stay in that original position. You were already moving in a forward direction. When you took a right, your body will tend to fall or stay in that direct line. So if I draw a line, we're drawing this way, then somebody takes a sharp left, your body was going forward in the forward direction. So your body wants to stay that way, which is why you all fall to that direction. Okay. Dislodging ketchup from a bottle when you're hitting it on the bottom, by moving the bottle, you're trying to get that ketchup to fall to the bottom, because by slamming it down, you're moving its position and you want it to fall. All right. Headrests, again, you have those headrests in the back of your head in your car. When you slam to a stop, if there's no headrest like my chair, your neck flies back, and that causes major issues with your neck. So we'll check this video out in class, and I'll have some questions and answers that I want you to do along with it. Okay, so again, high-speed car crashes. We're going to talk about this. This is really relevant after we went to Indianapolis Speedway. So you should check this out. Okay, mass of inertia. Okay, here's some new information that you need to start writing down. So if you haven't started yet, I reviewed some old stuff. Mass of inertia. This should be the title. So we're setting up Cornell notes. It should be Newton's TLNS first law, mass and relative motion. So if you've been just listening before, I want you to be writing this down now. Newton's first law, mass and relative motion. Okay. Okay, apparently. So the more mass an object has, the greater its inertia, the more force it takes to change its state of motion, okay? So if you have an elephant, it's going to be really hard to move it, right? Compared to like a baseball sitting on the table. Baseball, I can push it easily and it'll start to roll. The greater the mass, the greater its inertia, so aka the more force it takes to get it into motion. Okay, inertia depends on mass. Mass can become a measurement, or is a measurement of inertia. Okay? Kicking a can. An empty can is fairly easy to kick. A heavier can or rock is going to hurt your foot. If you kick a boulder, it's not going to be likely to move, but it will hurt your foot as a reaction. Okay. Very important key things to note, maybe something to write over on the side in your Cornell note style. Mass, not volume. Mass is the amount of matter in an object, okay? See, I say it down here. Mass on a matter in an object is how much stuff, how many atoms make you up, okay? Whether I smush you like a bug or you stretch yourself way out, you still are made up of the same amount of atoms. So you can change your volume. You can curl up in a ball when you're like riding on a bus. So some of you who curled up in a ball, or like if you're sharing a bed with somebody, again, you sprawl out and you take up more volume. But ultimately, that's a measurement of space. Unit of mass is kilogram. Mass is not weight. Weight is the force of gravity on an object. This is really important. Guarantee it'll show up on a test. Mass is inertia. Okay, mass is the quantity of matter in an object. I said that. Okay, so let's look at this. The pillow has a larger volume, but a smaller mass. This weighs less than this. There's a button on this pen. This little battery thing does not have a lot of weight. Or this little battery does have a lot of weight while the pillow does not. Duh. So it's going to be harder to pick up the battery than the pillow. You throw that pillow at somebody, easy to chuck it across the room. Battery takes a little bit more effort. Okay. Important things to note. 1 kilogram, 10 newtons. 1 kilogram, 10 newtons. All right. So, and we also know 1 kilogram is 2.2 pounds. So you can kind of do your math here. This would be nice to know for dimensional analysis purposes. So 1 kg is equal to 10 newtons is equal to 2.2 lbs. Okay, so if this came up, then I told you somebody weighed 175 pounds. How many newtons are they? You were going to have to do that conversion. Well, you know, 2.2 pounds is 1 kilogram. I guess we could have just done 1 newton. So you could do 10 newtons. And now you can find that pounds. Okay? This is why I taught you dimensional analysis. It's important to know how to convert all these units. Okay? 175 pound person, multiply it by 10, 1,750 pounds, divide that by 2.2, 1,700. Apparently I'm going too far to the edge of this thing. That's why it keeps going out of here. Sorry, I can't write anymore off to that side. Okay, standard in SI units. We've talked about this at the beginning of the year. Mass is kilograms, force is in newtons. Okay, 1 kilogram bag of nails weighs 10 newtons. All right, 1 kilogram, 10 newtons, 2.2 pounds. Great. Always on Earth's surface, force of gravity is less. Away from Earth, the force of gravity is less. So the bag of nails would weigh less. So again, weight is how much gravity affects it. So that's going to make a difference no matter where you are. Okay, this is relative motion. This tends to throw people off a little bit. Okay, objects move with the Earth. Okay, right now you're sitting here watching this video, right? In your head, you're not moving, right? You're sitting there, you're sitting still. I'm sitting here still in my chair, not moving. Well, in reality, the Earth is rotating, and you are on that Earth. So if you were not moving, you would be like hit in the face with your house. See, there's a wall over there. Yeah, if I were not moving, one of these walls would hit me as the Earth continues to move. So even if I jump off the ground, I'm still continuing that motion. Okay, so a good example would be hold up. As I walk, I can walk and toss the ball, and the ball moves with me. I don't know if you could have heard that. It's hard to see. I don't have a lot of kicking toys. Okay, so let me explain what I was trying to show you in my little tiny window of space. This ball, as I walk, if you've ever done that, like you walk and toss the ball up, whether it's a football, a crossball, a baseball, a wiffle ball, whatever. As you toss it up, because you are moving, if you're walking down the street, if you toss it up, it's moving with you. So that's why it falls back into your hand. All right? It doesn't fall over there. doesn't fall over there. It falls right back in your hand as long as you're moving. Now, if you were walking and then started running, that's going to change the situation. But as long as you're at a constant motion, dynamic equilibrium, if you toss that ball up, it's going to land in your hand while you're moving. Same thing on the bus. You guys were just on the bus for a long time. If you threw things on the bus, it was as if you weren't actually moving, even though the whole bus was going about 50 miles an hour the whole time. Okay. So, here you go. I talked about this already, but here you are standing on the earth, apparently up near North Pole-ish, Alaska-ish. Okay, you're hanging out. You jump up so your feet are not touching the ground anymore. Why? The earth is rotating at 30 kilometers a second. That's kind of fast. How come you don't get hit in the face? Because you move with the earth. When you jump up, you're already in motion, just like in the bus. If you were to jump up while we were driving in the bus, you jump up and land on the bus. You don't move or you don't fly to the back of the bus because you are already in motion. You are already moving with the bus. Your speed was actually 60 or 55 miles an hour, whatever the bus was going. All right. So looking around at the people on the bus, it doesn't look like you're moving. But someone out on the street watching you sees that you are in fact moving at 60 miles per hour. Okay. So we move as the earth moves. Same thing. I went over this. You flip a coin, you toss a ball, etc., etc. While in a moving vehicle, they're going to move as if you were at rest, even though you're moving at high speeds, whether it's in an airplane or the buses we rode to Dayton. Okay, this is important. We're going to utilize this information later. So, for safety, places that are high risk of having earthquakes, they'll put weights in their building to help stabilize. So in Taipei, on the 87th floor, there's a 3 million kilogram steel ball that just hangs there. Okay, if you think about it, we have our tall building, ready? And about right here, we hang a steel ball. Why is that? To provide this staying force. The more mass in the middle upper level section of the thing, the more mass, the less likely it is to sway when the earth begins to sway. All right, we're going to talk about that more later. Okay. So same thing. If wind starts blowing it, it's going to take a lot more effort.